Hi everybody. I hope this video will help to clarify some of the issues that some of you are having with dealing with vectors. Many of the topics that you do include vector quantities, and you need to know how to deal with them so that wherever they appear and you have to work with vectors, it won't be a nightmare. So in this video, we're going from scratch, starting with what we mean by a vector quantity as opposed to a scalar quantity. Meaning of the terms we often use: parallel, antiparallel, perpendicular, oblique, resultant. We want to look at what those words mean in relation to vector quantities. You should know how to find the resultant of two or more vectors by calculation. At some levels, calculation is emphasized, while at some levels, scale drawing is emphasized. So we want to look at both methods of finding the resultant of two or more vectors. First of all, a vector quantity has both magnitude and direction. Magnitude simply means size. So a vector quantity has size and it has direction. And some examples are force, velocity, momentum, acceleration, displacement, and there are others. So it doesn't matter which vector quantity you're dealing with. What we're doing in this video will help you to deal with any vector quantity. It's a basic rules governing how we deal with vectors. Scalar quantities do not have direction, they only have magnitude. So, like mass, temperature, time, energy, distance, speed, electric potential, and so many others. So, because vector quantities have both size and direction, we have to take both features into consideration. Let's take force for example. It's not just important to pay attention to the size of a force, but the direction in which the force acts will make a difference in terms of the effect that the force has. This ball sitting on this box, if you apply a force of a particular size in that direction, it will not have the same effect as if you apply the same force in another direction. What happens to the ball eventually will depend not only on the size of the force, but the direction in which the force is applied. Different directions, even though it's the same size force, will have different effects on the ball. So direction is always important when you're considering vector quantities. A vector quantity is represented by what is called a directed line segment, simply meaning a part of a line with an arrow. The length of the line represents the magnitude or the size of the vector. The direction that the arrow is pointing in represents the direction of the vector. So if you draw the line and have no arrow on it to show direction, you have not fully represented the vector quantity. All these lines here have different lengths and different directions. So they are all representing different vectors. These lines also represent different vectors. They all point in the same direction, but they have different sizes. So even though they have the same direction, because they have different magnitudes, they're all representing different vectors. For two vectors to be equal, they must have the same size and the same direction. These don't have the same sizes, so they are not representing the same vector. These have all the same size, but they're all pointing in different directions. So again, All of these represent different vectors. For two vectors to be equal, they must have the same size and the same direction. Speaking of directions, how do we specify the direction of a vector? Most times we don't have a problem representing the size of the vector. The length of the line can be measured or calculated, and that gives us the size of the vector. But how do we indicate the direction of the vector? One way we can do that is to use the cardinal points. So if we have a reference system, if we're using the cardinal points as our reference, then we can choose to use north, south, east, west to indicate the directions of these vectors. What if it's something in between? Between north and east, we can call that northeast. But careful now, there's only one specific direction that we call northeast, and that's exactly halfway between north and east. It means then, because we know the angle between north and east is 90 degrees, it means then that if a vector is pointing northeast, then it must be 45 degrees north of east, or 45 degrees east of north. It's exactly halfway between north and east. So if this angle here is not 45 degrees, you cannot call this direction northeast. If it's even off by 1 degree, it is not northeast. Similarly, southeast is exactly halfway between east and south. Northwest is exactly halfway between north and west. And southwest is exactly halfway between south and west. So if any of these angles here is not 45 degrees, we cannot name these directions as northwest or southwest or southeast. What if it's halfway between those? So halfway between north and northeast, we have north northeast. The angle, half of 45 degrees, 22.5. So if the angle here is not 22.5, we cannot call this direction north northeast. And that goes again for all the other blue lines that you see here. We can only use these labels if the angles correspond. So east southeast must be 22.5 degrees on the south side of east. Or if you're going from south, using south as your reference, 90 minus 22.5, 67.5 degrees on the east side of south. Okay, so this is limited in some respects, or if we have to specify a direction that is neither north northeast nor northeast, let's say it's just a few degrees on the east side of north northeast, it can get a little technical. The best thing to do is to specify exactly what the angle is in relation to a known direction. So we can identify the direction of this red line here, representing a vector, as 62 degrees north of east. Meaning, if you're starting with east as your reference and move 62 degrees on the north side of east, that's where this vector is pointing. 62 degrees north of east. Of course, you could also look at it as 28 degrees east of north. Okay? Similarly, this purple vector here could be described as having being in the direction 7 degrees south of west, meaning you're on this using west as your reference, you're 7 degrees below west, on the south side of west. So in using the cardinal points, could have challenges if the direction we want to specify does not correspond to any of the standard directions that we are familiar with. So it's best to use the angles. Use the angle that the vector makes with another direction that is known. The x and y axes of the coordinate system are sometimes useful references to specify the direction of a vector. So we could determine the angle that the vector makes with the positive y-axis, or with the positive x-axis, or with the negative x-axis, etc. We could determine the angle that this vector makes with the positive x-axis or with the negative y-axis, depending on which angle you choose to specify. We could use the x and y coordinate system as reference directions to specify the direction of a vector. Sometimes we don't have that much information. Sometimes we're only given the direction of a vector relative to another vector. So for example, we may be told that vector r makes an angle of 50 degrees with vector v. All we know is that the angle between them is 50 degrees. And that may be enough for the purpose for which we are specifying this vector. So it doesn't have to be cardinal points. It doesn't have to be the coordinate system. It could just be another vector that we have some information about. Whatever the case is, a vector is not fully defined, not fully represented, unless you state both its magnitude and its direction. Speaking of angles between vectors, let me just spend a little time here to make a few points. When you're identifying the angle between two vectors, those two vectors must start from a common point. Looking at this diagram, it's obvious that the angle between these two vectors, r and v, is 50 degrees. Over here, I have the same two vectors, same r and same v. Not just because I've labeled them r and v, but because this r is the same length as this r, and it is pointing in the same direction as this r. So these two are parallel. So they're equal because they have the same size and they're pointing in the same direction, the two r vectors here. The v here has the same length as this v, so same magnitude, and it points in the same direction as it was over here. This v is parallel to this v. So this line is representing the very same vector that we had over here, but it's just that I've drawn it at a different position on the page. Because we move r and v from over here to over here doesn't mean that the angle between them has changed. The angle between this r and this v is still 50 degrees because you're going to measure it here. Because like I said, when you're identifying the angle between two vectors, those two vectors must start from a common point, or they could both point towards the same common point. If we put the r here instead, it becomes obvious that this angle is 50 degrees with the two vectors going towards this common point. Over here, they're going away from the point. Here, they're coming towards the same point. The angle between them, this angle right here, is 50 degrees because it is opposite to this angle. The point I'm making is you couldn't look at this diagram and say the angle between R and V is 130 degrees. Where did that 130 come from? 180 minus 50. So the angle on this side is 130, but that's not the angle between the two vectors, because for this angle, V is coming toward this point, R is going away from this point. So this would be incorrect. To say that the angle between both of them is 130 would be incorrect. The angle between them is still 50 degrees. Because here it was 50 when they're going away from the common point. It's 50 when they're going towards the common point. And it's the same two vectors. So changing their position on the page doesn't change their position relative to each other. If we should change the direction of V so that it now looks like this, same length, but the arrow is pointing in the opposite direction, it's not the same V. It's not the same vector that you had before. This would be negative V because it's pointing in the opposite direction. So looking at R and this line, which is negative V, the angle between those two would be 130, not the 50. So the angle between these two vectors is 50. They're coming from a common point. The angle between these two vectors is still 50. Here is not the same two vectors. R is the same, but this is not the V that you had before. Because even though it's the same length, if the direction of the line has changed, it is not the same vector. So this vector is making an angle of 130 degrees with R. This vector is making an angle of 50 degrees with R. I hope that makes sense. So if you are not given a diagram and you are just told that the angle between two vectors is a particular value, when you're making a sketch, you must draw those two vectors going away from the same point or coming towards the same point in order to correctly identify the angle between them. So let's look at some of the words we use to compare directions. Parallel means that the vectors have the same direction. You may have heard it said, parallel lines never meet, and that's true. No matter how you extend those lines, they never meet because the distance between them is constant. They never get closer together, they never get further apart. There are some people who sometimes misunderstand that statement and interpret it to mean parallel lines do not meet. There's a difference between saying the lines do not meet and they never meet. Because if you have two lines that are not meeting at the moment, they do not meet. It doesn't necessarily mean that they are parallel. They are not meeting now, but if they do not have a consistent distance apart, then if you extend them, they might eventually meet. This might be obvious, but just to make sure that everybody's clear on this, these two lines do not meet. They are not meeting at the moment, but they are not parallel because they do not have a constant distance apart. So the distance between the lines here is obviously smaller than the distance between the lines down here. So that's why they are not parallel, because they do not have a constant distance apart, not because they do not meet. If they are extended, they may eventually meet somewhere out here because they're getting closer and closer together. So they will eventually meet. Hence, they are not parallel. Parallel lines never meet. So parallel vectors have the same direction. Antiparallel vectors are in opposite directions. And remember, we're talking directions here. It doesn't matter if the lengths are not the same. Parallel and antiparallel, those terms relate to the direction of the vector, not its size. By the way, the angle between parallel vectors is 0 degrees, and the angle between antiparallel vectors would be 180 degrees. Perpendicular vectors are at right angles to each other. So the angle between them is 90 degrees. And it doesn't matter how you orient them on the page, as long as the angle between the vectors is 90 degrees, we describe them as perpendicular. And notice again that the arrows are pointing away from a common point. Oblique is the word we use to describe vectors that are neither parallel, antiparallel, nor perpendicular. So if the angle between the vectors is not 0, 90, nor 180 degrees, then we describe those vectors as being oblique. So the challenge usually comes with combining vectors. We cannot add vectors like how we add scalars, because the direction is going to make a difference to the result. Scalar quantities can be added algebraically. So 3 kilograms mass plus 4 kilograms mass gives you 7 kilograms mass. No direction involved there, just magnitude. However, for vector quantities, it's different. For vector quantities, we use what we call vector addition. So 3 plus 4 gives you 7 for scalars, always. 3 plus 4 could give you anywhere between 1 and 7 for vector quantities, depending on the angle between them. So 3 plus 4 can give you 5 if it's vectors you're talking about. So when we combine two vectors, we are finding what we call the resultant vector. The resultant is a single vector that has the same effect as a combination of vectors. So if we have two vectors here, these two arrows representing two vectors acting on a point object, when we find the resultant of those two vectors, what we're finding is one force that will have the same effect by itself as the other two forces that were there before. So to find the resultant is to replace the two or more with one that has exactly the same effect. It won't be the same size as the other two. It won't have the same direction, but it has the same overall effect as the other vectors that you combined. So let's look at how we combine vectors. There are two methods that are commonly used. We can find the resultant vector by calculation or by drawing to scale. I want to look at the method of calculation. So adding parallel vectors is pretty straightforward. The magnitude or size of the resultant is the sum of the magnitudes of the vectors that you're adding. And the direction of the resultant is the same as the direction of the vectors that you're adding. Because if the vectors are parallel, they have the same direction. So the direction of the resultant is the same direction that you started out with. So we have this vector here represented in green, 4 units long, and we're adding to that another vector here in blue, 3 units long. The resultant is represented by the vector in pink, and it is 7 units long. So 4 plus 3 gives us 7, and they're all pointing in the same direction. So let's say we use displacement for example. This is like saying, okay, if we're starting from a point and we walk 4 meters in one direction, and then an additional 3 meters in the same direction, then our overall displacement from where we started to where we end is 7 meters in that same direction. So that's parallel. For antiparallel vectors, we subtract the magnitudes of the vectors to get the magnitude of the resultant. And then to decide on the direction of the resultant, it would be the same as the direction of the larger vector. If we have vectors 3 units and 4 units now, but in opposite directions, our resultant is no longer 7. Our resultant is now only 1 unit. And the direction of the resultant is the same as the direction of the larger force. So the 4 units is larger. The direction of the resultant will be the same as the direction of the 4 unit vector. So we got 7 when they were parallel. We're only getting 1 now when they're antiparallel. It's like if you take 4 steps in one direction, and then when you get to the end of that, you take 3 steps in the opposite direction. Your final displacement is only 1 step. So these are 2 examples that you can do. You can pause the video, work them out, and then continue to see what the answers are. The addition of perpendicular vectors will require you need to be familiar with Pythagoras' theorem and trigonometric ratios, sine, cosine, and tangent. So let's just insert a few reminders at this point. If you have a right angle triangle with x and y as the perpendicular sides and r is the hypotenuse, then according to Pythagoras' theorem, the length of r squared is equal to x squared plus y squared. So if we know x and y and we want to find r, we simply square x, add it to the square of y, find the square root of that, and that would give us r. So when we're adding perpendicular vectors, which would be represented like our x and y here, the magnitude of the resultant is obtained using Pythagoras' theorem. And although this is not a scale drawing, we still use a sketch as often as possible. And notice in this sketch how the arrows are pointing. This y vector here is pointing down, x is pointing across, starting from where y stopped, and the resultant is starting from start to finish. So this is sketched using the triangle arrangement. Meaning, if we're adding two perpendicular vectors, the two vectors to be combined are drawn tip to tail and they form adjacent sides of the triangle. So where the blue vector ends, the green one begins. The tip of the blue to the tail of the green, those are the two vectors you're adding. The resultant, the direction of the resultant is from the first tail to the last tip. So this red line here has to be pointing in the direction shown. If it were pointing in the opposite direction, that would be a wrong direction for the resultant. So even though the length of the line would be the same, the direction of the resultant would be wrong. Remember we said if it's not the same direction, it's not the same vector. So though you may get the size correct, the wrong direction will make the answer wrong. If you're not sketching according to the triangle method, then you can use the parallelogram method. In that case, the two vectors to be added are drawn from a common point and form adjacent sides of a parallelogram. The resultant vector is a diagonal of that parallelogram, drawn from the same common point. So if this is where we start drawing our vectors, with the green and the blue starting from the common point, the resultant must also start from that common point. So all the three vectors are pointing away from the common point. You could not draw the resultant this way, from this point to this point. That would be wrong. It would be the wrong direction, even though it would have the same size. Note that the parallelogram is just two triangles. So these three diagrams are representing the same two vectors being added. The first one here, they are drawn according to the parallelogram method, starting from a common point with the resultant from the same common point. Here, if we start with the blue and then add the green, the resultant is from where we started here to where we finish. If we draw the green one first and then the blue one following in that direction, the resultant is from where we started with the green, the tail of the green, to the tip of the blue. So, and of course, if you put these two triangles together, you get back a parallelogram. So any of these three diagrams could be used as a sketch for the same two vectors that we're adding. Notice the red lines, they're all parallel, they're all the same length. So they all represent the same resultant because it's the same two vectors we started out with. We end up with the same resultant regardless of which way we sketch the diagram. So as we were saying, the size of the perpendicular vectors, and this only works for perpendicular vectors. We find the size using Pythagoras' theorem, and then now the direction is given as an angle, the angle between the resultant and one of the original vectors or another known direction. So based on the diagram we have here, we could give the direction of the resultant in terms of angle theta. So the resultant r makes the angle theta with vector x. Notice they're both going towards this point. So theta is the angle between them. Or you could specify angle alpha here as the angle the resultant makes with vector y. Both y and r are coming away from this point. So alpha is the angle between y and r. And based on our trig ratios, tan theta would be y over x, opposite over adjacent, and tan alpha would be x over y. So you could use either angle. whether alpha or theta, to give the direction of r, but you must specify that it's the angle r makes with x or the angle r makes with y. A quick example: two perpendicular forces of 7 newtons and 12 newtons act on a point object P. Calculate the resultant force on P. No diagram is given, but you will sketch a diagram and make reference to that diagram in your answer as necessary. So all we're told is that the two forces are perpendicular to each other. So we make a sketch, not drawn to scale, just labeled accordingly, 7 newtons and 12 newtons. And we want the resultant of these two vectors. We can use this line to represent the resultant that we're going to calculate, drawn from this point P, since the other two vectors also started from P. So we're trying to find the size of R and the angle R makes, whether with the 7 Newton or the 12 Newton, to specify the direction of R. We could sketch the diagram another way. If we drew it using the triangle method instead of the parallelogram method, draw the 12 followed by the 7, the resultant direction would be from start to finish. Very similar to what we had before, same size and same direction we would end up with, no matter how we orient the vectors, because we're going to find the direction of the resultant in relation to one of the two original vectors. So since the original vectors serve as our reference, however we turn the triangle on the page, we will end up with the same answer. Same size resultant and same angle that the resultant makes with one of the original vectors. So let's go. Since the vectors are perpendicular, the magnitude of the resultant, and this is how we represent magnitude of the resultant. Using Pythagoras' theorem, the magnitude of R is 13.9 newtons, square root of 12 squared plus 7 squared. The direction, if we're finding angle theta, then opposite to theta is a 12 newtons, adjacent to theta is a 7 newtons, so 12 over 7 gives us tan theta, and theta is 59.7 degrees. So we can round off those values to two significant figures, since we didn't start off with more than two significant figures. So our answer is 40 newtons at 60 degrees to the 7 Newton force. We can't just say 40 newtons at 60 degrees. We must specify 60 degrees to what? So it's 60 degrees to the 7 Newton force, because that 60 degrees that we calculated is the angle between the resultant and the 7 Newton force. Or we could have found the angle alpha, which is between the 12 Newton force and R. So tan of alpha would have been opposite, which is a 7, over the adjacent, which is a 12, since the 12 is adjacent to the angle alpha. The 7 is opposite to the angle alpha. And our answer there would be 14 newtons at 30 degrees to the 12 Newton force. So far we have looked at combining parallel vectors, antiparallel vectors, and perpendicular vectors. What do we do when the vectors are oblique? And remember, by oblique we said we mean not parallel, not antiparallel, and not perpendicular. So for oblique vectors, what we do, first of all, is to resolve each vector into two perpendicular directions. What do we mean by that? When we resolve a vector into perpendicular components, what we do is to treat the vector that we start with like the resultant of two perpendicular vectors. So if this is a vector we want to resolve, we want to find the two components that are at right angles to each other that we could add up to give us this resultant. If that's the vector to be resolved, you're trying to find the two perpendicular components that would form the other two sides of a right angle triangle. Okay? So that's what you're trying to do when you're resolving a vector. You're starting with one vector and trying to break it up into its two perpendicular components. So it's like the reverse of what we did with adding perpendicular vectors. When we were adding perpendicular vectors, we start with two perpendicular vectors, we combine them and we get one resultant. When you're resolving a vector, you're starting with one vector and you're trying to break it up into two perpendicular components, which, if you added, would give you back the resultant that you started with. Looking at the trig ratios one more time. If Vx and Vy are combined, they are perpendicular, and they are combined to give us vector V, and theta is the angle that vector V makes with Vx, then we know that Vy over V is sine theta. And if we rearrange that, making Vy the subject, then Vy is equal to V times sine theta. So just simply rearranging this, that sine theta is Vy over V, making Vy the subject, Vy is equal to V times sine theta. Similarly, if Vx over V is cos theta, and remember that cosine is adjacent over hypotenuse, so if Vx over V is cos theta, rearrange this equation, make Vx the subject, we get Vx is equal to V cos theta. We need that to help us resolve a vector into two perpendicular components. So generally, if this vector V, represented by this red line, is the vector we want to resolve, then when we sketch where those two perpendicular components would be, they should form acute angles with the vector we're trying to resolve. And based on our knowledge of trigonometry that we just looked at, the component that is adjacent to the angle is going to be V cos theta, and the component that is opposite to the angle would be V sine of the angle. If you're using the angle alpha on the other side instead, then the green line here would be the side that is adjacent to the angle. So the green line is your V cos alpha, and the blue line would be V sine alpha. So somebody might be looking and say, so where's the triangle? Remember that if you put this green line over here, draw the green component on this side, here's your triangle. It's still opposite to theta. This angle would be alpha, the green line would be adjacent to the alpha. So whether you put it on this side or you put it over here, it's the same vector because it has the same length and the same direction. So this component is v sine theta or v cos alpha, depending on which angle you're using. This component is v sine alpha because alpha would be down here, and it is v cos theta if you're using theta. So somebody might be wondering, is v cos theta the same as v sine alpha? And is v sine theta the same as v cos alpha? Yes, because the theta and the alpha are complementary angles. Those are angles that add up to 90 degrees. Because remember, our components are perpendicular, so the theta and the alpha add up to 90 degrees. And for complementary angles, the cosine of one is the sine of the other. So here, if we have this vector representing 16 meters at an angle of 49 degrees to some arbitrary reference direction, if we want to resolve these 16 meters into perpendicular components, with one of them along this line and the other perpendicular to our reference direction, how would we calculate what these components are? Well, since this green line is adjacent to the 49 degrees, it is going to be 16 cos 49. 16 is the V, 49 is the angle. 16 is the size of the vector, 49 is the angle it makes with this direction. This component would be 16 cos 49. And the next component would therefore be 16 sine 49. So those would be your two perpendicular components. And we can calculate the value as necessary. Here's another example. 0.9 meters per second is the vector we want to resolve. So we're given its size and the angle it makes with some reference line. We want two perpendicular components, one along this reference line and the other perpendicular to it. The two components, what are they going to be? You can pause and think about it before you look at the answer. Since this component is not adjacent to the angle, not next to the angle, it's going to be sine 57 degrees times the 0.9, which works out to be 0.75 meters per second. Same unit that we started out with. So the other component here along the reference direction is going to be 0.9 cos 57, which works out to be 0.49. So these are the two components of our original vector. If you want to check if you are right, imagine if you had these two components to add, these two perpendicular vectors to add. To find the resultant, you would use Pythagoras. So you would say 0.75 squared plus 0.49 squared equals r squared. Work it out. You'll see that you get back 0.9 as the size of the resultant. One more example. 5 newtons at 32 degrees to this reference line. We want to find the perpendicular components of that. Have you come up with your answer? The component adjacent to the angle is going to be 5 cos 32, and the component opposite to the angle in question is going to be 5 sine 32. Of course, in both of these cases, you could have used the angle that is not labeled, calculate it and use it, you would still get the same result in the end. So 90 minus 32, which is 58. So you could have worked this out as 5 cos 58 and this one as 5 sine 58. So that's how we resolve a vector into two perpendicular components. That was step one of calculating the resultant of oblique vectors. So the other two steps is simply to find the resultant vector in each of the perpendicular directions and then combine them to find the overall resultant vector. Let's do an example. Find the resultant of the vectors shown. We have three vectors here. 5.2 units at 64 degrees to this direction that we can call x, 9 units at 17 degrees to that same direction, and 6.4 units opposite to that reference line. Our aim in combining these vectors is to produce one vector or resultant to represent all three, and it will have a magnitude and it will have a direction. This one vector can be thought of as having perpendicular components. So if we can find the perpendicular components Rx and Ry and combine them, we can find our resultant. So starting with what we're given, we can resolve our original vectors here into two perpendicular directions, and it's convenient to use the reference line here as one, which we'll call x, and perpendicular to that we're calling it y. So first we resolve our vectors. The 6.4 units is already along this line where x is, so we don't have to resolve that. This has no y component. We can resolve the 5.2 units. It is neither along y nor along x, so we can resolve that into two perpendicular components. Those red lines represent the components of the 5.2 units. How do we calculate these components? Based on the 64-degree angle, this one would be 5.2 cos 64 because this component is next to the angle 64. This component would be 5.2 sine 64. Resolve the 9 units. One component will be along x and the other will be along y here. What are the sizes of these components? This will be 9 cos 17 because it's adjacent to the angle of 17 degrees. This one will be 9 sine 17. Once we have determined our components, we no longer need the original vectors. So this is what we have now. We started off with 3 vectors, but now we have 6, but they're all parallel or perpendicular to each other. So the two red ones have replaced the original 5.2 units vector. The two blue ones have replaced the original 9 units vector. The 6.4 units did not need to be replaced because it was already in one of the perpendicular directions. So now all we have here are parallel and perpendicular vectors. Step 2 said find the resultant vector in each of the perpendicular directions. And these are the components of the overall resultant vector. So Ry, which is the y component of our resultant, is going to be the sum of what we have in the y direction. 5.2 sine 64, 9 sine 17. They are in opposite directions, so they are anti-parallel. So we're going to subtract them. 5.2 sine 64 minus 9 sine 17. And since our sketch here is showing us the Ry pointing upwards, we're going to assume that the 5.2 sine 64 is the larger one. If when we subtract them, we end up with a negative answer, all it means is that the Ry is actually pointing in the opposite direction. So we will just redo our sketch. Similarly, in the x direction, we sum all the vectors in the x direction to give us the x component for Rx, the x component for our resultant. So 5.2 cos 64 plus 9 cos 17, because those two are parallel, going in the same direction, so we're going to add them. And we're subtracting the 6.4 because that is opposite to those two. So in the x direction, we have 4.49 units. That is our Rx. So now we have reduced everything to just two perpendicular components, Ry and Rx. And we can use Pythagoras to add them. So the magnitude of our resultant R is the square root of Rx squared plus Ry squared. And that gives us 4.9 units. So that is the magnitude of our resultant R. And the direction of R we can find based on the angle theta. So tan theta is Ry over Rx, Ry over Rx, 2.04 over 4.49, and we do the inverse tan of that to give us the angle theta, which is 24 degrees. So our answer is 4.9 units at 24 degrees to the x direction. It has a magnitude and a direction, so it's fully specified. If we should include our resultant on our original sketch, it's 4.9 units. This is where R is. And the angle it makes is 24 degrees to the x direction. What if we wanted to give the angle in relation to one of the original vectors? No problem. If R makes 24 degrees with x, and the 5.2 units vector here was at 64 degrees to x, then the angle between R and the 5.2 here is just 64 minus the 24, which is 40 degrees. So the angle between R and the 5.2 units is 40 degrees. We could specify that angle. Or what if you wanted to find the angle that R makes, the resultant makes, with the 9 units vector? It makes 24 with x, and the 9 unit also makes 17 with x. So you would add those two angles to get the angle between R and the 9 units. 24 plus 17, 41 degrees. What if we wanted to state the angle that R makes with the 6.4 units vector? Between R and the 6.4 would be, work it out, 180 minus the 24. because the 6.4 units makes 180 with x, and r makes 24 with x. So the difference there would be 156 degrees. I hope that these objectives have been achieved and that this video has shed some light on vectors as it relates to physics. Hopefully, you'll no longer be scratching your head in despair whenever you hear the word vectors.